Hello everyone. My name is Nabi Hussein. I am a refrigeration sales engineer for Doran USA. We are the USA branch of Doran Innovation, off-scene Mario Doran. That's in Italy. I'll do today's presentation is CO2 transcritical compressors, design, lab testing, and the safety of devices that go along with them. This is the Doran family. At the very top will be Mario Doran. He is leading the company currently, and his son, Giovanni Doran, he will be North American operations. His brother is over China operations, and then his cousins also work in production. So it's a family-owned, family-run company. Quick introduction, HQ, Florence, Italy. Everyone is welcome to come and visit at any time. They love hosting anyone who wants to go visit, and it's a beautiful city as a backdrop. Um, all of the compressors that are manufactured for the USA will come from our factory in Florence, Italy. There is also a few factories in China, but they only cater to the local market. And then we have sales offices throughout Europe, Russia, China, and South America. So 200 employees, 4 production sites, 5 sales offices. Annually, as of 2022, we made 75,000 compressors. That number has gone up. Um, it's just to meet the market demand. But today's uh, webinar is to go over the CO2 compressor and CO2 in general as a refrigerant. So carbon dioxide, it could be called R744. It has a GWP of 1. That's because all other refrigerants are measured against it. So it's definitely a future-proof, sustainable refrigerant. Has excellent heat transfer properties, high COP levels, um, and some would describe it as the perfect refrigerant, but it does have severe challenges from the compressor perspective and some of the other components. Some important conditions, the critical point, which just means when you go into supercritical fluid, that's at 1070 psi and 87.8 F. Um, so just 87.8 F, you can see that it's very easy to reach transcritical CO2. The triple point is at 75 psi and negative 69.8. That's where solid, liquid, and gas can exist. And the main issue there is dry ice. Low temp evap operation is usually around 180 psi, negative 25 F. Medium temp is negative or around 420 F. So for operators, those are the conditions you would keep in mind. And condensing happens at 1031.5 psig and 86 F. Just some things to keep in mind, and all the design and test criteria I discuss in this presentation is based off of our 4412 CFH 160 horsepower compressor. It was our largest until we made a larger one. CO2 safety, mostly a safe refrigerant. I mean, at 1%, you have breathing rate increase up until 4 to 5%. You're looking at an intoxicant effect. 5 to 10%, you should be able to notice the smell, but it's described as a very sterile smell. Um, Loss of consciousness may happen within minutes, and then 10 to 100% is unconscious after prolonged time and possible asphyxiation. So, for the most part, very, very safe, but it is good to be cognizant of the dangers. This is the CO2 pH diagram, very similar to any other refrigerants you would work with. Um, and then this is a superimposed CO2 flash gas bypass system. Um, Number one is where you're entering that flash gas bypass tank. But what we will be focusing on is number 6 to 8, which is the low temperature compressor, and then 9 to 10, which is the medium temperature compressor, which will go into transcritical CO2. Here is our compressor as an example. You have the suction service valve right here. You have the electrical box, the nameplate, very important to know where that is, and always look at nameplates whenever you look at a compressor. Oil sight gap, oil sight glass, you check that to make sure that you have 1/4 level oil. Um, some other compressors may suggest 2/3. Ours is 1/4 of that sight glass. The oil pump, depending on the size of the compressor, if it's a smaller size, you may not see that. It might use a splash disc on the inside. High pressure relief and then low pressure relief, you can't see it, but those will be on every compressor. A discharge temperature sensor, and right here's a discharge service valve. So you come up to a compressor in the field, you see one, this is what you're going to see, and these are the insides. Main things to know is the terminal plates. Your supply power goes into the compressor. It powers the motor, which is a rotor and a stator, which converts that electrical energy into mechanical energy through the crankshaft. That crankshaft, while it's spinning, it's moving the pistons, the rods and pistons, to compress low temperature, low pressure CO2 into high temperature, high pressure CO2. Gets accumulated in the it gets accumulated in this discharge, and then it goes out to either your gas cooler or a condenser. It does come with challenges, as we mentioned. CO2 has a much larger pressure differential than other refrigerants. Um, just based off of these numbers, you see 1,066 psi differential for CO2. It's 6.5 times higher. Um, but this just means that your compressor needs to be able to handle that. We believe reciprocating technology works best with this, but there are other technologies that also work for high pressure differentials. CO2 has the high volumetric refrigeration capacity, which if you have more refrigeration capacity, you can have smaller pipes, smaller bores, but that has less room for the stress unloading, and that increases your specific load. So the positive comes with a drawback, and that drawback is visualized here. You have your discharge plenum, your valve plate, your cylinder wall, and that piston is connected to the rod by that wrist pin. And that wrist pin is what takes most of that specific load. So something as small as a wrist pin needs to have a lot of design thought behind it in a CO2 compressor. Here's the PSIs you would consider for R404A. 1566 PSI would be the specific load on that wrist pin, but when you go up to CO2, it's around 5,000 PSI. And it's 3 times the load, 5 times the load, whatever it is. You plan for that wrist pin to handle that load, and if it fails, then the compressor fails. High discharge temperatures is the next thing that is a consideration in the design of CO2 compressors. For HFCs, you're looking at 196 as a normal discharge temperature. And if you saw anything higher than that, you would think something was going wrong. But with CO2 standard operation, you're looking at around 311 degrees Fahrenheit. Um, the challenge that this poses is you have to figure out heat dissipation for the compressor, and you also need to figure out proper lubrication. So those are the two challenges we're going to focus on: design improvements to a compressor and validation uh, for making a compressor work in a CO2 application. Here's some general recommendations we have. They apply to our ranges, but it could be any of the other ones. we would really say stick to boundary conditions when you're looking at a compressor sizing, but you're looking at 320 degrees as your discharge temperature, making sure your oil never exceeds 145 degrees, and that you always have superheat at your suction. So the quickest way to destroy a compressor is to have liquid enter into it. And that's why we have that 18 degrees of superheat, but there's also the maximum of 55. We said lubrication was a challenge, and that's because the oil that we use for CO2 compressors, the CO2 is very soluble in it. So where you would see an R134A in a POE 55 system, you have 98% oil with 2% mixed in. But with CO2 and POE 85, you have about 93% oil. That's 7% of the CO2 dissolved into it. That leads to lower residual viscosity of the oil, less of it being able to lubricate the system. It leads to the higher oil recirculation rate. But the main thing is CO2 is a detergent. So if you have liquid CO2 inside of your oil and it goes upon any metal surface, it's going to clean it. And now you have metal to metal. So, sorry, 1 second. Okay. So as a detergent, you want to make sure everything inside the compressor is lubricated. You have CO2 that is dissolving in your oil and you're trying to deal with all these tribology issues. Here are two designs that we have because we do make semi-hermetic reciprocating compressors for HFCs and CO2. So we had our internal discharge plenum design. Um, this came with the problem that that internal discharge plenum it gives heat to that oil, right? It's heating up that internal oil, and we have that constraint of keeping the oil cool, so the residual viscosity is higher. And we have our external discharge plenum. Same thing, same compressor functionality. You're taking the internal and you're moving it externally, leading to a thermal cut between the high pressure and the low pressure sides, lower heat dissipation towards the oil sump. This is how we're dealing with that first challenge of lubrication. And then here they are side to side. The theory behind it is dissipate the heat exterior instead of interior. Here's a side view of the compressor. You can see suction gas will come in through the suction. It'll cool down that motor, and it will also pick up some oil droplets of the oil that's coming at the last bearing of the crankshaft. In our previous design, those oil droplets would be pulled into the suction holes of the valve plates. So we added a internal casted partition, kind of stop those oil droplets from being pulled in. You're side by side the designs. Not something people would see, but it's the thoughts that have to go into designing of this CO2 compressor to work as efficiently as possible and have the least possible oil carryover. This is a typical test lab setup. So you have the compressor, you have all of these sensors, and the control valve. So whether you're trying to turn off oil supply, um, this is how we set up our testing lab. Closed circuit, it's not actually giving any cooling load, but it has a sink for that cooling load. Here it is visually. So you can see the 160 horsepower compressors off there to the right, has the supply power going into it, and then sensors all over it. Gas cooler is on the outside. The only high pressure, high temperature part of a CO2 system is going to be the discharge between that discharge valve and the gas cooler. Everything else is low temperature, low pressure. We test at three different points to validate our designs. Number one is max pressure ratio, which is the ratio between suction and discharge pressure. The challenge it has is you'll see the max discharge temperature at this point. Max pressure differential would be the next point we test. 1500 psi discharge, 285 at the suction. The challenge you see is max load, and then we test it at typical empty conditions, which I think is the most interesting for people to see those conditions. For every compressor we validated, it's 2000 hours continuous running, which isn't a very long time to run a compressor, but it does remove any youth issues that you would see in a compressor's design. And then we run it 200,000 times, short cycling, 5 seconds on, 5 seconds off. So we did our very best to try and destroy our compressors in our factory so it doesn't happen in the field. And here you see the results of comparison of performance and reliability. The most important thing is here, notice that your oil temperatures, 167, 158, 155, with the internal discharge plenum, you're much cooler with an external discharge plenum, 125, 118, 113. Um, it might seem intuitive just to be like, well, why did you have to check and see that? Well, you need to validate designs, but this compressor with an external discharge manifold has the ability to keep cooler oil, which leads to residual viscosity of the oil being higher. That leads to more reliability because that oil is lubricating the internals. So that's the thought process with CO2 compressors. It's always about what can we do to make sure that these harsh conditions of high temperature, high pressure, and oil are maintained so the compressor will continue to function. Here are examples of wear on the wrist pin and nowhere on the wrist pin. What you want to see is that nowhere whatsoever on a wrist pin. We did the same to validate the oil carryover being lower as an internal design. So you wouldn't actually see it when you come up to a compressor. Just know that the technology is inside it. It's the same test setup. So what we did is we turned off all oil returning to the compressor. So it can only run as long as possible without oil returning to it. Once the oil carryover has reached a point where it trips its oil pressure sensor to cut off the compressor to protect itself, this is how we tell is there low oil carryover. So we did see an improvement with the internal partition. It did give it an extra maybe 15 minutes, 15 minutes of runtime, and that's 15 minutes longer in the field where someone can resolve an issue. This troubleshooting section, I have brought it down a little bit from my typical at an NASRC event, we would go into this troubleshooting section and that would be coupled with a compressor teardown. But I've brought this section down to just typical safety devices you would see on a compressor. So if you come up to a compressor, first thing, you look at the nameplate, it will tell you what oil it's using. It'll tell you its max load, amp draw, quick things to check, and then the oil sight glass to make sure that the oil level is at 1/3 of that. But the protection devices on it is motor protection. Right here, you can see these two little prongs going up. That's a sensor that connects directly into the motor. And when that trips, it means your motor is overheating. So it turns off your compressor to protect the motor. An oil pump, it's a gear driven it's a gear-driven oil pump. It's going to be pushing oil into your compressor. It is used along with the oil differential pressure switch. Once it senses a low differential pressure, you know that you have lack of oil, lack of lubrication. It would shut off your compressor. We have a crankcase heater, which is used to keep the oil temperature um, above the point where liquid CO2 would be inside that crankcase, inside the oil sump. And that's so on startup, you don't have liquid CO2 flashing off inside of your metal surfaces. There's the low pressure, high pressure relief valves. The low pressure relief is set at 1,349 psi, and the high pressure relief is set at 2,030 psi. Um, so those are to protect the actual compressor itself from overpressurizing. All of these safety devices, they only work if they are electronically connected in series with each other. And I bring it up only because if you bypass any of these safety features, they no longer protect the compressor. So typically, the Cree1 INT 69 motor protection will be installed on every compressor. It seems to be what has come out as the industry standard. Um, it's a PTC sensor that's embedded in each of the windings. Once you reach a certain temperature, it turns off the compressor. There's a max discharge temperature sensor, similar functionality, but now it's set off of a max discharge temperature. If it's a smaller compressor and it doesn't have an oil pump, it's going to be using an optical oil level sensor. So it's looking at the little pocket that's holding the oil next to the splasher disc. If it sees oil, it's fine. If it doesn't see oil, it turns off the compressor. And then the oil differential pressure switch, it's looking at about 12.3 psi plus or minus 2. If you remember from that graph you saw where the compressor kind of cut off, that's when the oil pressure fell below that 14.3 psi for longer than 90 seconds. Then the crankcase heater, we suggest this where compressors would spend a long time um, off, and then on startup, you have CO2 liquid inside the oil sump. So this, just before you do the startup, you heat up that oil sump to bubble out that liquid CO2. Here's an electrical connection scheme of the safety devices. Again, all of these safety devices only work if they're connected and connected properly. So I would usually take everyone out to tear apart a compressor, see its insides, maybe spin the crankcase a little bit, see the bores, but this will be where our presentation ends today.